Okay, I'm going to get started. There are 9 lectures from the start of the semester to test 1. Those 9 lectures are all on electricity. We've actually covered in the first 3 lectures the complete theory of electricity. So we talked about electrical charge as being a dimension of nature that is the origins of electricity. We talked about the electrical field as being a kind of mediator or a carrier or a conveyor of electricity. And we talked about Coulomb's law, superposition principle for electrical forces. So those 3 classes on those 3 topics, charge, field, and force, are the complete theory of electricity, what I should carefully call electrostatics. They're the complete theory of electrostatics. What we're going to do over the next 6 classes before test 1 on electricity is, I've listed it here, we're going to try and deepen our understanding of electricity by thinking of electricity in new ways. Thinking of electricity in new ways, for example, thinking of electrical energy. We're going to look at some of the emergent properties from the theory of electricity. One of the emergent properties that we'll look at is electrical circuits, which is very important to us. And then we'll also work on our problem solving in electricity, our methods, our techniques for problem solving in electricity. So I think what I'm saying is we've already done the complete theory of electrostatics. What we're doing now is deepening our understanding of electrostatics. We're going to be doing problem solving in electrostatics, and we're going to look at all the amazing things that come out of, emerge from electrostatics. So that's basically the plan. Okay, today's class. I want to introduce these quantities. So these might be new words, but I mean they're not completely new words to us, but their physics meaning might be new words. I'm going to talk about sources, sinks, and flux. I'm going to define, first part of the class is to define and introduce the quantity we call electrical flux. I'm going to define charges as sources and sinks, these new words of electrical flux, and a law that's associated with that, Gauss's law. And then as we move through this, we're going to look at examples of the relationships between this new quantity, electrical flux, and more familiar quantities, electrical field and electrical charge. So that's basically the plan. Okay, so starting with the first part of the class, which is concept of electrical flux, idea of electrical flux, how it's defined, also how it's related to these words of sources and sinks. What are sources and sinks? So here's a little sketch to introduce us to sources and sinks and flux. On the left-hand side here, I've got an example of sources and sinks and flux involving water. And I took this at home. This is my kitchen sink. And we'll discuss this example of sources, sinks, and water and flux. And then over here, I've got the analogous example for sources and sinks and flux of electrical field, And they're entirely analogous. They're entirely equivalent. Just one is kind of the concrete case of water flowing around. The other is the more abstract, unseen case of the electrical field flowing around. I should say that there's beyond physics, using the words source, sinks, and flux. All sorts of sciences and beyond use sources and sinks and flux. So in ecology, right, areas of population growth might be sources of population, and areas of population decline might be sinks of population. In economics, right, production of goods is a source of goods, and consumption of goods, that's a sink of goods. So sources and sinks are used throughout science and beyond. Okay, so sources and sinks for the water example. The faucet is a source of the water in this picture. That's where the water is coming from. The drain is the sink of the water in this picture. That's where the water is vanishing. So faucet is a source, drain is a sink, and the flow, the flux of water, is the movement of the water, the flow of the water from the source in this picture, the faucet, to the sink in this picture, the drain. So we can see the water flowing around from the source to the sink. So that introduces source, sink, and flux for the water. We can think of electrical field in a similar way. This is a picture I showed in last class. It's this famous field line sketch of the electrical dipole. So electrical dipole, if you remember, is positive charge and negative charge, upstairs, downstairs. And it produces a very characteristic, a sort of very beautiful pattern of field lines surrounding it. Feels strong near the positive and near the negative charges, and falls off quickly as 1 over the cube of the distance as you move away from the arrangement of charges. But anyway, we can think of this in terms of source, sinks, and flux. So the positive charge, like the faucet, is a source of electrical field lines. They're emerging from the positive charge. The negative charge, like the drain, is the sink of field lines. They pour into the negative charge. And the field lines themselves show the flow of electrical field from the source, the positive charge, to the sink, the negative charge. So we're seeing that flow from the positive charge upstairs here down towards, we see all these field lines mapping out this flow towards the negative charge. And so that's source, sink, and flux. So flux is a new abstract quantity reflecting the flow of the field to add to that original abstract quantity of the field itself. Let me just compare flux and field, because they're two new abstract things. They're not things that we feel like forces, for example. So this is again the picture of the electrical dipole, positive charge on the left, negative charge on the right. The field lines, I've mapped them out again in this fantastic pattern here. On this diagram, I've marked in purple a location where I'm thinking about the electrical field. And I've also marked in green here a surface where I'm thinking about the electrical flux. So we're going to compare this point upstairs here where I'm thinking electric field with this point downstairs, this surface downstairs here where I'm thinking electric flux. And this is a key point in comparing these two. So when we think about electrical field, I'm thinking about some point in space, and I'm thinking about the field at that point, that particular point in space, that field having some strength at that point, that field having some direction at that point. And so on that sketch, that purple arrow is my representation of the electrical field at that particular point in space. When I think of flux, I'm thinking of some surface in space. So you see I've drawn for flux a rectangular surface, the profile of a rectangular surface. And I'm thinking of the number of field lines through that surface. That is the flux. And so in the case of flux, I don't think about point, I think about a surface in space. And in the case of flux, I don't think about how closely packed the field lines are as the strength of the field, or the direction of the field lines for the direction of the field. Rather, I think about how many field lines. Are there a lot, or are there just a few that are passing through that surface? Because that represents the flux. Importantly, the field is a vector quantity, so it has a size and a direction. The flux is a scalar quantity. It just has its size. It can be positive or negative, but it doesn't have an orientation, a direction. Okay, here's our definition of the electrical flux. Our quantitative, precise, mathematical definition of electrical flux is defined through this equation here. I'm using the symbol phi for flux. I added a subscript E on it because it's electrical flux. And we'll meet other fluxes, for example, throughout the course. So phi E is our electrical flux. The equation, to think about this equation, look at the picture. So in this picture, I've got the two ingredients that we need to calculate an electrical flux. I've got an electrical field, and I've represented by the electrical field by electrical field lines in orange that sweep from upstairs on the left to downstairs on the right. So we see that electrical field represented by the field lines. We also see a surface, a rectangular surface, a sort of brown rectangular surface, and that's the surface that the field lines are passing through. And I've represented that by this vector here. This vector here, I called it A because it represents the area of the surface. It has a length that represents the cross-section of the surface, so how many square millimeters, or how many square centimeters, or how many square meters the surface is. And it also, importantly, has a direction. So you notice I drew it at right angles perpendicular to the face of the surface. That's the direction of the surface vector that represents that surface. So it tells us actually how the surface is orientated, whether the surface is horizontal or whether the surface is vertical or some other angle would be indicated by the direction of the vector A. It represents the orientation of the surface. So that vector A not just tells us the size of the surface, but the orientation of the surface. So the flux is defined in terms of thinking about the electrical field vector at the location of the surface and the vector A that represents the surface. And the flux is defined in the following ways. There's two ways we sometimes write it. One is to say that the flux is simply the product of the area of the surface, how big it is, times the component of the electrical field that's perpendicular to the surface. So the part of the electrical field that is perpendicular to the face of the surface. So that's one way we write it. More often, I think, I would write it like this. The flux, the electric flux through that surface is the size of the electrical field over the surface. So that's the E here, and that's the size of the electrical field. The area of the surface, the size of the area of the surface, that's the A here in this equation, times multiplied by the cosine of an angle, cosine of theta, and that angle theta is the angle between the two things in flux, field and area, that have orientations, directions to them. So the field has a direction, the area has a direction. They're both represented by vectors, and cosine theta is the cosine of the angle theta that's between the vector E and the vector A. And so that cosine theta bit accounts for the relative orientations of the electrical field and the surface immersed in the electrical field. And all those three bits go together to make the electric flux. If you want to visualize flux, it's actually often very helpful to be able to just look at a picture and visualize the flux through a surface. The trick is that the flux through the surface is just represented by the number of field lines that pass through the surface. So if you've got some surfaces and some electrical fields, you can just count the field lines, and that's proportional to the flux through those surfaces. So that's a way to get a visual picture of a flux through a surface. But we're going to look at some calculations of flux through surfaces. So I got 3 slides here. I'm going to go through them pretty quickly because whilst there's kind of a lot of information on them, lots of little calculations on them, each one is just conveying one basic point about flux, about how flux depends on the field strength, about how flux depends on the area of the surface, about how flux depends on the relative orientation of the field and the surface. So they're all just doing that. I don't know if you know Roadrunner. When I grew up, I mean, essentially that's all I watched was Roadrunner at 8 or 10 hours a day. And I put the Roadrunner on here because I'm going to go fast through these slides. I'm not going to go through all the details of all the calculations on these slides because I'm really just trying to convey points that the flux depends on the field, obviously, depends on the area, obviously, depends on the orientation in the field in the area, also kind of obviously. Okay, so this slide here is just an illustration that the flux depends on the area of the surface. I've got a uniform electrical field in this sketch here. It's represented by the blue lines that streak from the left to the right. That's my picture of the electrical field lines. I've got a big, medium, and small surface in this field. And so the flux through the big surface is big. The flux through the medium surface is medium, and the flux through the small surface is small. And I worked out for all the numbers that I put on this plot, the areas of the different surfaces, the strengths of the electrical field, what the sizes of the big flux, the medium flux, and the small flux were. I'm not caring too much about the numbers right now. I'm just saying that flux depends on the area of the surface. And you can see it here. We said we could imagine flux by counting the field lines through the surfaces. Look. Big surface, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 field lines go through that, a lot of flux. Medium surface, 1, 2, 3, 4, 5, 6, 7, maybe 8. Medium flux through that surface. Small surface, 1, 2, 3, 4, 4 lines going through that surface. So that visual inspection of the number of field lines through the surface also tells us that, you know, we've got a big flux over here on the left, a small flux over here on the right. Move on. Flux also depends on the field, of course. And that's what this slide is depicting. Again, I'm not going to go through all the numbers on this slide. You can take a look at that later if you want more punishment. But I want to describe the fact that the flux depends on the field. Over here on the left-hand side, I've got a region of strong field. Look, the field lines in blue are closely packed. Over here on the right-hand side, I've got a region of weak field. Look, the field lines are weak, loosely packed. In between the left and right, it's sort of a medium field. The field lines are less closely packed than the left. They're more closely packed than the right. So strong field, medium field, weak field. I got the same surface in each of those 3 regions. Same area surface, same orientation of the surface in those 3 regions. And so what would we expect? In the large field here, then we expect a large flux through this surface. In this small field here, weak field here, we expect a small flux through this surface. And in between here, in this moderate field, we got a in-between flux through this surface. And so this slide is just demonstrating that the flux also depends on the field. Again, we can see it by counting field lines through the surfaces. I got 1, 2, 3, 4, 5, 6, 7, 8 through this surface here. That's the large flux. I got just 1, 2, 3 through this surface over here. This is the small flux. And then downstairs here's the calculation. Last one. Okay, so this may be slightly less obvious. I mean, it's very obvious that the flux depends on field, very obvious that the flux depends on area. But it's also important that it depends on the orientation of the area in the field. That means it's important that it depends on the relative orientation of the vector E and the vector A that describe the directions of the electrical field and the orientation of the surface. So look at this one here. In this one, I've got a uniform electrical field. That was the first slide I showed. I've also got a same area surface. That was the second slide that I showed. So the field strength's the same everywhere. The area of the surface is the same everywhere, but actually I've got very different fluxes through the three surfaces it's just because of the orientation. In this one, over here on the left, right, the field, which goes from left to right, is actually parallel to the vector A that represents the surface. So there's 0 degrees. Theta is 0 degrees between E and A here. In this one in the middle, the field is still going left to right. The surface is horizontal, and so the area vector that's perpendicular to it is actually pointing downwards here. So it's actually 90 degrees between the vector E and the vector A in this little sketch here. And then finally over here I picked some other case, right? That's neither the field lines perpendicular to the surface or parallel to the surface. This is somewhere in between, and I've calculated the flux through this somewhere in between surface. This has the largest flux because the field lines are perpendicular to the surface. This actually has no flux because the field lines just sort of skim above the surface or skim below the surface. They don't pass through the surface. And this is somewhere in between. At this angle, you're somewhere in between the largest flux and the smallest zero flux for this size surface in this size electrical field. And again, you can see it if you count the field lines. I've got 1, 2, 3, 4, 5, 6, 7, 8 through this surface here. There's none through this surface here. Look, this one here maybe just skims above the surface. This one here skims below the surface. They don't punch through the surface. And then this one over here, which is at an angle, I got 1, 2, 3, 4, 5, 6 field lines through this surface. So flux also depends on the orientation of the surface in the field, depends on the angle theta. If you want, just to lighten the mood, if you want to think about flux in other situations, cars on a highway. If you stood by the highway and counted the number of cars passing by you, then that would be a flux. And actually, you know, in this highway here, you've got a positive flux on, say, on this side of the road, with the cars moving from the top to the bottom of the picture. You would have an opposite flux, a negative flux on this side of the road with the cars moving from the bottom to the top. Flux is important, as I said, in water flow. So here's a picture of some random part, I think, of the Columbia River in Washington. But what's interested in is that through each of these little rivers or streams or brooks or whatever you actually call them in geography, there's water flowing, and there's different fluxes of the water flowing. If we could count the molecules of water passing by a certain point as a function of time, we could determine the flux in all the streams and brooks and creeks and rivers that are shown in this picture. Okay, demonstration of flux. Okay, what was I going to say? Got to remember to show everybody. in this prop here, I call it, the arrows here represent the field lines. So the metal bars with the arrows are the field lines. And this is a region of uniform electrical field, because those field lines, if you look, they're all pointing in the same direction. They're all equally spaced from one another. This is a region of uniform electrical field E. In this uniform field, I've placed two surfaces. One surface is this angled surface here, and the other one is this vertical surface here. So there's two surfaces in here. Now, these two surfaces in this uniform electrical field, well, they have different areas. That's obvious, right? This one's smaller, and this one's larger. So they have different areas. They also have different orientations. The smaller area surface is at right angles to the field lines, whereas the larger area surface is not at right angles to the field lines. It's at some other angle. Maybe it's about 45 degrees. Both surfaces actually have the same flux through them. And you can see that if you count the number of field lines that pass through each of the surfaces. The same number of field lines pass through the smaller surface as pass through the larger surface. So they have the same flux through them, but they do have smaller or larger areas. They do have different orientations, but the combination for these two particular surfaces with these two areas and these two orientations actually yields the same flux. And so that's a demo of flux. Okay, let's look at an example calculation. Oh, sorry. So now we got, imagine a 1 centimeter by 1 centimeter cube that's immersed in an electrical field. Now this, I've enlarged it for this demonstration, and I've distorted it because this isn't a cube either. But imagine this 1 centimeter by 1 centimeter by 1 centimeter cube immersed in an electrical field that I switched on in this room before class. So that's the situation. We've got to figure out the flux through the 1 by 1 by 1 centimeter cube in a particular electrical field. Actually, we're given a number for the electrical field strength. Is 500 newtons per coulomb is the field strength. And we're also given the direction for the electrical field. If you look here, it's along the x direction. So it doesn't have any components in the vertical y direction or in the out of the screen z direction. It's all in the x direction. So what's the flux through that? You might already know the answer. I mean, the answer is the total flux through that cube is actually 0. I sort of immediately know the answer to that, and you're going to learn to see immediately, if you didn't already, the answer to that. It's zero flux. But I'm going to, as an example of flux, I'm going to go rather quickly through actually laboriously and boringly calculating the flux through the 6 faces of the cube. So the cube has a top and a bottom, it has a front and a back, and it has a left and a right face. We're going to go through calculating the flux through all of those 6 faces. Again, this is a Roadrunner example. I'm going to go through the numbers very quickly because I don't want to be dragged down into the boring number calculation. I want to keep it on the level of the concepts and the ideas of calculating the flux through this surface. Okay, so this slide is where I calculate the flux through the top, the bottom, the front, and the back. So 4 of the 6 faces. So the vector A on the top and the bottom, remember it's perpendicular to the surface. It represents the surface. It's either pointed up for the top or down for the bottom. There's a convention that we use. It points out of a surface that is closed. It points, and by closed I mean a closed surface. So there are what's called open and closed surfaces. A closed surface is one that you can define an inside and you can define an outside. So a closed surface, supposing I'm inside this box here, right? And it's made of I don't know, something I can't get out of, tungsten. I'm inside and I can't get outside unless I was to, break the box. If you're outside, you can't get inside a closed surface without breaking through the walls of the box. For an open surface, this was 2 open surfaces. I can go from one side of a surface to the other side of the surface just by walking around the corner. I can go from this side to this side just by walking around the corners. So that's two closed surfaces, open surfaces. This is a closed surface. Anyway, for a closed surface, there's a convention that the vector A points out of the closed surface. So upstairs on the top, it's going to point upwards. Downstairs on the bottom, it's going to point downwards. At the front face here, it's going to point towards you. Back face is going to point away from you. So those are the four orientations. So what's the flux of the electrical field through these four surfaces, top, bottom, and front and back? It's actually zero in every case. It's zero in every case because if you think about it, you can think about the equation for the flux if you like. I laboriously wrote it down 4 times here. In this equation is the field strength, which is non-zero everywhere. In this equation is the area of the surfaces, which are all non-zero for these 4 surfaces. But also in the equation is theta. It's the angle between E and A. And for these 4 surfaces, it's always 90 degrees. The electric field E, the area A, always at right angles to one another. And cosine of 90 degrees is 0. It makes the flux 0. If you think about it, visualize the field lines. No field lines go through the top face. No field lines go through the bottom face. No field lines punch through the front face or the back faces. There's no flux visually through those 4 faces. So they're all 0. The 2 faces that do have flux but through them are the left and the right-hand faces. And I pictured those 2 faces here. So here we are going to see some net flux through those 2 surfaces. Remember, the convention is that the vectors A point out of a closed surface, so the face over here on the right is pointing towards the right. Face over here on the left is pointing towards the left. The equation for the flux is the field strength times the area of the surface times the cosine of the angle between the field and the surface. I'm calculating it for the right-hand surface, this one here, the left-hand surface, this one over here. In both cases, the field strengths of this 500 newtons per coulomb. In both cases, the areas are the area of the faces, 1 centimeter by 1 centimeter, which is 10 to the minus 4 square meters. In the 2 cases, the 2 vectors, E and A, are either parallel to one another, that's this case on the right, so the angle's 0 degrees, or they're opposite one another, that's this case on the left. A is towards the left, E is towards the right. So the only difference in these 2 calculations for the left and right-handed faces is either using 0 degrees for the right-hand face, the orientation of the 2 vectors, or 180 degrees for the orientation of the 2 vectors in the left-hand face. The only difference that results then is that one flux is positive, 0.05 Newton meter squared per coulomb. The other one is negative 0.05 Newton meter squared per coulomb. The positive one just means that the flux is kind of coming out of the cube. The field lines are coming out of the cube. The negative flux means that the field lines are going into the cube. They're heading into the interior. So plus and minus for a closed surface denotes whether your field lines are flooding in or your field lines are flooding out. If they're flooding out, positive flux. If they're flooding in, that's negative flux. Okay, what's the final flux? The final flux then is 0, right? We had no flux through top, bottom, and front and back. We got equal and opposite fluxes through the left and right-hand faces. And so if we add all those fluxes up, the total is 0. There's no net flux through this cube that's immersed in a uniform field. And we could have imagined that, right? Every field line that goes in to the cube for a uniform field must come out. Every one that goes in has got to come out. It means that that means that the next net flux through that closed surface is 0. Actually, we couldn't have calculated the following questions. What is the flux through, in that uniform field, not through a cube, but through some random shaped blob? well, I can't calculate the flux through a random shaped blob because it's just such a weird surface. I can't describe it mathematically. It's an impossible problem. But no, you can calculate it, or you can think it out, because in a uniform field, no matter what the shape of the surface, whether it's a nice simple cube or it's a random shaped blob, every field diagram that goes in at one location must come out at another location. So the overall flux through the random shaped blob, just like the overall flux through the cube, in a uniform electrical field is going to be 0. Okay, so that was an example of flux. I want to move on to Gauss's law. And how Gauss's law, sometimes also called flux law, how flux law is related to electrical fields and electrical charges and field properties. Okay, so here's a picture of Gauss. So I better get in a little bit of history, because I know everybody really wants me to spend time on the history and not on the problem solving. So I want to get in a little bit. Gauss, a very famous mathematician, very famous scientist. They called him the Prince of Math. Gauss came up with, you remember Coulomb's law? That was a couple of classes ago. And so this is kind of the weekly anniversary of the Coulomb's law class. And we're meeting Gauss's law, which is actually an equivalent to Coulomb's law. It's written in a very different way. It's written in a very different fashion. But they both describe how electrical forces work. So Coulomb's law, which you've already met, Gauss's law, which you're about to meet, both describe the workings, the nature of the electrical force. So it's quite kind of interesting. It reminds us that is, you know, in physics or science in general, there's often not just one way of describing how something works. There's often multiple ways of describing how something works. And those different ways of describing how something works, sometimes one's more useful, sometimes the other's more useful. And that's true here. Sometimes Coulomb's law will be more useful, sometimes Gauss's law will be more handy. Okay, enough of that. Here's Gauss's flux law. Let me state it first in words, because it's a nice one to state in words, I think. It says that the flux, and by that it means total flux or net flux, through a closed surface. Remember, a closed surface has an inside, has a definite outside. And you can't get from in to out or out to in without breaking through the surface. The flux through a closed surface is simply in proportion to the charge inside the closed surface. Gosh, this is a really simple idea. That flux phi through a closed surface is in proportion to the charge inside the closed surface. Now, when I say in proportion, to make it concrete, we want a proportionality constant between the flux and the charge, between the flux through and the charge inside. And there's two ways of writing that. Here is the flux. Here's the charge inside. And one way of writing the proportionality constant between the flux and the charge inside is, in terms of the Coulomb constant, is 4 pi times the Coulomb constant. So that's a version of the flux law, Gauss's law. There's another way you can write it in terms of a equivalent constant. It's called the electric permittivity. I really have trouble spelling it. But electric, not the electric bit, but the permittivity bit. You can write the flux law as the electric flux being equal to the charge inside divided by the electric permittivity. So either of these you can use. And Coulomb constant and electric permittivity, we kind of just tend to use them, you know, whenever it's most convenient. Like somehow I can always remember Coulomb constant, 9 times 10 to the 9, so that's a good thing, I can remember it. I have harder problem remembering the electric permittivity, though, or I've taught this enough now that I do think it's 8.8 times 10 to the minus 12 in SI units. So I can remember those numbers. In this case here, I don't have to keep multiplying by 4 pi if I use the electric permittivity. In other cases, if you use the electric permittivity, you might have to divide by 4 pi. So, you know, there's pros and cons. here's a picture. So we've got it in words, we've got it as an equation, but I always like the pictures best. In any book, I always like the pictures best. Here's a picture of Gauss's flux law. It says the flux through this is the kind of strange shaped blob here that happened. And the flux through this strange shaped blob that happened is represented by the number of field lines. And the number of field lines that pass through the surface of the strange shaped blob is in proportion to the charge inside. And so that's a picture of Gauss's law. Look, I drew a positive charge here with the field lines coming out. That makes a positive flux. I could have drawn a negative charge with the field lines coming in. That would be a negative flux. So positive or negative flux immediately tells you, if it's a closed surface, whether there's negative or positive charge, net charge, inside the closed surface. So that's a very handy idea. Okay. So my spouse is from Wales, and you might know what's Wales famous for. Wales is famous for the only country that ever had more sheep than people. And so I'm always thinking about sheep. And in this overhead, we're going to imagine that, so this is to help us imagine Gauss's law, the flux law. And we're going to imagine that it's not electrons that have charge, it's not protons that have charge, but in this world, it's sheep that have charge. So charge is owned by sheep. Now, this is going to be a picture of Gauss's flux law. So here's a charge, this sheep on the right. Here's another charge, this sheep on the left. And here's a closed surface, the pen. The flux through the pen, the flux through that closed surface, is determined by the charge inside the pen, the sheep inside the pen. It's not affected by, the flux through the entire closed pen is not affected by the other charge, sheep, that's outside the pen. So that's a very important point. When you think about an arrangement of charges, and when you think about a closed surface in the field of that arrangement of charges, the flux through that closed surface, total flux through that closed surface, only include the charges that are inside the closed surface. Exclude the charges that are outside the closed surface. The ones inside are going to determine the flux. The ones outside make no net contribution to the flux. Didn't explain this. This happened in the previous class too, because I'm a big Lady Gaga fan, have been for decades. So she sometimes comes to class. She comes to class when there's a fundamentally important idea. This is a fundamentally important idea about the working of electricity, that electric charges are the source of electrical flux. It's a new way of thinking about charges. I'm glad she brought it up. So we think about in physics that electrical charges are actually sources or sinks of electric flux. The more charge, the more electric flux. Specifically, the more positive charge, the more positive electric flux is being sourced by that charge, and the more negative charge, the more negative electrical flux is being synced by that charge. So think of charges now like the faucet for a positive charge, like the drain for a negative charge. They're where the flux starts, they're where the flux ends. And so that's a really deep understanding that's in Gauss's law that we never met when we talked about Coulomb's law. And so that's why Lady Gaga came to class. Okay, let's look at, I wanted to show you, I said that Gauss's law and Coulomb's law are actually different versions of different ways of expressing the same interaction. They both describe electrical interactions, and I wanted to show you how they're linked. I got one slide on that, and then we'll turn to some more examples, illustrations. Where am I going? Here. what am I doing on this slide? What I am doing on this slide is showing you how you can turn Gauss's law, which is about electric flux, into Coulomb's law for the electrical field, which is about electrical field. So on the left-hand side of this slide, I'm going to go through this little sort of calculation where I start with Gauss's law, and I'm going to end up with Coulomb's law. Now, the calculation involves the following basic problem. I've got an electrical charge here. I made it a positive charge to be concrete, so plus Q, plus uppercase Q. It's, as we now know, a source of electrical flux. Here are the field lines that emerge from that electrical charge. And I'm going to figure out, based on the flux law, the field at the location of this spherical, this is an imaginary spherical Gaussian surface, we would call it. This is drawn in 2 dimensions. It's as a circle, but it's really a sphere that's perfectly surrounding, perfectly encasing that charge at the center of the sphere. So what's the field at the location of the surface of that sphere? That's an interesting question, and we're going to figure it out actually using our new tool, Gauss's flux law, the flux law. Okay, so here's Gauss's flux law. Flux through the closed surface, which in this case is a perfect sphere, is in proportion to the charge inside the sphere, this charge plus Q here. Let's start with that, and let me fill in my understanding, my notions of what flux is. We spent the first 20 minutes on this. Flux is defined in terms of the field and a surface. It's the strength of the field times the area of the surface times the angle between E and A, the 2 vectors describing the field and the surface. So I plugged all those things in. E is the strength of the field. I put the vertical lines because I wanted to be clear. I'm just thinking about the size. A is the area of the surface. It's the area of the sphere here. And cosine theta, that's the angle between E and A. Now you might say, well, this is going to be hard. E and A point in different directions everywhere for this surface. Remember, above the charge, E's pointing up. Below the charge, E's pointing down. If you're on the left or the right, E's pointing left and right. So E's changing its direction everywhere. But actually, if you think about A being perpendicular to the surface, A is changing its direction everywhere. On the top of the surface, A's pointing up. On the bottom of the surface, A's pointing down. On the left and right, A's pointing left and right. So actually, although E changes its direction as you walk around the surface, and A changes its direction as you walk around the surface, the relative orientation of A and E, this is beautiful, they're always the same. They're always at 0 degrees to one another. Upstairs, E points up, A points up. Downstairs, E points down, A points down. So they're always at 0 degrees. Okay, so it's easy for me to plug in the area of the surface here. Remember this little bit? Remember high school? I don't. But apparently I did go. And I remember that the area of the sphere, 4 pi r squared. So plug that in. Cosine theta. Cosine theta, well, we just realized we were scared because E changes direction everywhere, A changes direction everywhere, but then we realized that theta is 0 everywhere. So plugged in 0 degrees. So again, remember high school, cosine theta, cosine of 0 is 1. So I plugged in those 2 things. I got this little equation here, and then I just quickly canceled out the 4 pi's divided by r squared. Oh my gosh, I've got Coulomb's law. Gauss's law just gave birth to Coulomb's law. And you can do the same thing the other way around. You can have Coulomb's law give birth to Gauss's law. They are equivalent descriptions of the same force. They're just different ways of describing the same force. It's an example, an illustration of how we use different ways in science to describe the same thing. Sometimes one's more useful, sometimes the other's more useful. Okay. examples of Gauss's law. Okay. In this sketch here, I've got a charge, it's a positive charge again. It's produced an electrical field, a very familiar electrical field that's strong close to the charge, weak far from the charge, emerges radially outwards from the charge. And then I've got three surfaces that are immersed in that electrical field. I've got number one, this sort of horseshoe-shaped surface. Now, again, be careful. This is my two-dimensional sketch of this horseshoe-shaped surface. But imagine the horseshoe has got a top and a bottom to it. It's really a three-dimensional surface I'm thinking of. That's surface one. Very complicated. Surface number two. That's just a nice, simple spherical surface. So again, I've drawn it as a circle, but it's a three-dimensional surface in a three-dimensional field. So that's number two. And then there's surface number three. It's also relatively simple. It's just a rectangular surface. I've drawn it as a two-dimensional rectangle, but it's really a three-dimensional rectangle. So the question says, as an example of fluxes and fields and charges, for us, it asks us to compare the total flux through the three closed surfaces, 1, 2, and 3. Now, at first sight, for various reasons, this looks like a very complicated mathematical problem. You'd have to be a math PhD to solve this problem. You'd have to be a math PhD to solve this problem because either you've got a very complicated surface that you would have to describe mathematically, or you've got the problem, the sphere isn't so complicated, but unfortunately, if you look at it, the field is changing everywhere over the surface of the field. It's stronger on the left, it's weaker on the right, and it's changing direction everywhere over the surface. So that's complicated too. The same for the cube, or the rectangle, right? The rectangle itself is not so complicated as a surface, but the field changes everywhere over the surface. Very hard to figure out the flux. So we're never going to mathematically solve this problem. And we would never be able to do that. I would never be able to do that. Rather, we're going to solve it visually, pictorially, from our understanding of Gauss's flux law. Gauss's flux law says that the flux through a closed surface, these are three closed surfaces, depends on the charge inside the closed surface. How much charge is inside each of these three closed surfaces? There's actually no charge inside any of these closed surfaces. The charge is here. It's nearby, like the sheep was nearby the pen, but there's no charge in this pen, number one. There's no charge in this pen, number two, and there's no charge in this pen, number three. So the net flux, the total flux through those closed surfaces is zero. So they're all zero. Here's a quiz question. Let me publish it. Oh, I didn't publish it. Sorry. Okay, it's published now, I think.
It's unpublished.
It's unpublished?
Yeah.
Did I unpublish it?
Yeah.
Good job. This is another question about the concept behind Gauss's law. Again, we've got some arrangement of charges. Yeah, feel free to talk to yourselves and talk to others. I'm the only one that talks to myself. You've got arrangement of charges, you've got arrangement of electrical field, and you've got three surfaces, and you've got to compare the fluxes through the three surfaces.
I apologize. Tomorrow.
You broke my heart.
I know. Tomorrow, dude, I'll be there.
Yeah?
Tomorrow. I'm literally going to all melatonin ever. Just like
Okay, let me give you the answer. We've got an electrical field that's due to an arrangement of a positive charge and a negative charge, separated by some distance. It's the famous electrical field of the electrical dipole. That's the picture here. We've got three surfaces in that field, A, B, and C. A is this small spherical surface. Remember, I'm drawing a two-dimensional surface, two-dimensional circle, but it's representing a spherical surface. B is a bigger spherical surface, and C here, this is what's called an ellipsoid surface. The flux through A, B, and C, surfaces A and B and C, is determined by the net charge, the total charge in A, B, and C. In A, there's a positive charge, so it'll be a positive flux. In B, there's the same positive charge, so there'll be the same positive flux. In C, there's the positive and the negative charges. They're equal and opposite. They cancel one another out when we compute the flux through the surface, because there's no net charge in the ellipsoid surface. So the answer to this question is that A and B have the same positive flux through them because they have positive charge, net charge inside the surface. C, on the other hand, that's overall neutral inside the surface because it's a plus and a minus charge, and so that has zero net flux through its surface. Now I do want to make the point that, you know, even C, just like A and B, at certain locations on its surface, there is flux passing through the surface. There are field lines passing through C's surface, just like there are field lines passing through A and B's surface. It's just that for C, the number of field lines that go in is the same as the number of field lines that come out. Whereas A and B, there's more field lines coming out than there are going in. And you can see that on the picture, right? For A, it's all field lines coming out. Every one of these field lines is coming out from the inside of A. Through B, it's field lines. Look, all the field lines are coming out through B also. But through C, if you walk around C, imagine you're an ant. And you walk through, I mean, I don't know why you need to be an ant. So imagine you're just yourself. And you walk around the ellipsoid surface C. Over here on the left-hand side, you see field lines that are coming out. Over here on the right-hand side, you see field lines that are going in. And if we were to count them up, I won't bore you with that, if we were to count them up, as many come out as go in, because there's no net flux through C. Okay, let's do some quantitative example. Anybody from Egypt, Cairo here? No. If they did, if they were, they'd probably walk out. Because I've completely misrepresented what a pyramid is. This pyramid here, in this picture, is made of 4 equilateral triangles as the sides. That's not what a pyramid looks like. But anyway, for this example, this is a physics pyramid. It's called a tetrahedron. If you look, there's a left-hand face, a right-hand face, a bottom face, and a back face, and they're all equal-sized, equilateral triangles. So it's a 4-sided object with 4 equal-sided faces, and at the center of it, I placed a charge, a 1.6 nanocoulomb charge. And the question is, what is the flux, total flux through the physics pyramid, not a real pyramid, and what is the flux through each face, or one face of the pyramid? So let's see if we can calculate that. I'm going to use the, whatever this thing's called, to do this. So there's 2 parts to this question. What is the flux through the entire pyramid? What is the flux through any of the 4 faces of the pyramid? We'll do both of those. Flux through the entire pyramid. The flux, according to Flux law, is 4 pi k, that's the proportionality constant, times the charge inside. I've left off all the subscripts. That's just sort of a combination of laziness, and you wouldn't be able to read them anyway. Well, we know the charge inside, and I know Coulomb's constant, so I can just plug in those numbers and make this calculation. So it's going to be 4 pi times 9 times 10 to the 9 is the numerical value of Coulomb's constant in SI units. It's newtons meter squared per coulomb squared, times the amount of charge, which was, what was it? It's forgotten what it was. 1.6 times 10 to the minus 9. 1.6 times 10 to the minus 9 coulombs. So just plugged in those numbers. Well, this is a nice example of where it was handy to use the Coulomb constant, because that's got a 10 to the 9 in it, and this got 10 to the minus 9 in it, so I can just do away with the 10 to the 9s. All I got to do is multiply 4 by pi, by 9, and by 1.6. So 4 times pi is roughly 12. 12 times 9. That's well, call it 10. So 12 times 10 is 120. Times 1.6, that's 180. And actually, if you do the calculation correctly, it's 181. So it's 181 newtons meter squared per coulomb. That's the units of flux, right? It's just the combination of the units of the Coulomb constant and the amount of charge. So that was easy enough. You know, try doing that with, you know, Coulomb's law. I wish he was here right now. Try Coulomb. Try doing that with your law. No way. What about the flux through a particular surface? One particular side. So I will use a subscript here, side. How are we going to do that? Well, here's how we do that. We make an argument about what it is. We make a symmetry argument about what it is. So the four faces were all the same shapes, all the same sizes, and the charge was at the center of the pyramid, so equal distance from all of the four faces. So that's what's called a symmetry, right? The faces all view that charge in a symmetric way. One's no different from the other in terms of viewing the charge. And so the four faces must share the total flux equally. One can't get more, one can't get less, because they're all the same distance from that charge. And so all I got to do is divide by 4 the total flux to get the flux through each face, or through one face. So it's 181 divided by 4, that's 45 and a bit. Newtons meter squared per coulomb. And so that's the solution to the physics pyramid problem. I want to talk about electrical conductors and electrical fields and electrical fluxes. So this is the last topic. This is the topic that part of it is something I didn't get to last class. I never get to it in that class, and so it always reappears as the ghost from the last class in the fourth lecture. Anyway. If I keep talking like that, I won't even get to it in this class. So I'm going to give you a rule. It's a couple of rules about electrical fields in the presence of conductors. And then I'll give you an example about electrical flux in electrical fields in the presence of conductors. So the first point is, and it's right upstairs here on this slide. Well, I've lost the pointer. When we talk about conductors, remember conductors carry charge freely through them. Metals are conductors, and salt water is conductors. When we talk about conductors, we actually talk about two kind of situations. One we call non-equilibrium and one we call equilibrium. The two sorts of electrical situations of equilibrium and non-equilibrium. In non-equilibrium, inside the conductor, if you could peer at the charges, the electrons or the ions, in non-equilibrium, they're all moving around. They're all rearranging themselves. So that's non-equilibrium, and these rules are not about that. The other situation is called equilibrium. That's if you look at the electrons, you look at the ions inside the conductor, they've all kind of calmed down and come to rest. They've all settled down. That's equilibrium. And so that's the situation for which these rules apply. There's 3 rules in equilibrium. And they're very important rules. They're very helpful rules in working with conductors. First rule is that inside a conductor in equilibrium, you know it's filled with charged building blocks, electrons and protons, but inside a conductor in equilibrium, the electrical field is zero. The charges have arranged themselves so that they cancel out the electrical field inside the conductor. It's like this desert of zero electrical field inside a conductor in equilibrium. So whenever you see a conductor in equilibrium, you could be thinking that inside that conductor, the field is zero. So that's one rule. If it wasn't zero, what would happen? If it wasn't zero, that electrical field would move the charges until it became zero. So that's why it is zero in equilibrium. The second rule is that on the surface of a conductor, think about the surface of a conductor, on that skin, on that surface, the electrical field that's just outside that surface, that's perpendicular at right angles to that surface. So this is another rule. Well, that sounds kind of strange. Why would it be that conductors do that? They make the electrical field just outside the surface, perpendicular to the surface. Why are they doing that? If they didn't do that, if there was a component of the electrical field that was in the plane of the surface, parallel to the surface, it would again move the charges inside the conductor. And they'd move around, rearrange themselves until they canceled out that component that was parallel to the surface. So that's why the field is perpendicular to the surface. And that whole stage of non-equilibrium is about the electrons or the ions moving around to cancel out the field inside and make the field perpendicular immediately outside. There's one other little rule that goes with that, is that inside for a conductor, it may be positively charged, it may be negatively charged, it may be neutral, but any charge regions, any non-neutral regions in a conductor are always on the surface. So if you've got a positively charged conductor, it must be positive charge on the surface. If you've got a negatively charged conductor, it must be negative charge on the surface. That is a rule. And so these are the three rules associated with conductors in equilibrium. Here's an example. The blue sphere is imagine I've got a giant solid gold globe. That's I have one at home, I didn't bring it. I've got a giant solid gold globe. That's a giant solid conductor. I've charged it up. I've negatively charged it. I've poured electrons from the Van de Graaff onto it. Those electrons, the excess electrons, they just reside on the surface. They have to live on the surface. The field of those electrons that are on the surface, they can't live inside the volume. That's against the rules. The field of those electrons just emerges perpendicular from the surface. There's no field inside. There's only field outside. And the field is perpendicular to the surface outside. So this is a picture that's showing you those three rules. And so that's very important. Okay. I think I'm going to end there. There's in my slides, there's one more example, and I put it as a video also, so you might want to take a look at that. An example of flux with conductors. Today's class, we talked about the words source, sink, and flux. We defined them. We talked about Gauss's law, Flux law, how it says that charge is source of flux, and we looked at illustrations, examples of Flux law and electrical flux. I'll hang out here if you've got any questions. I'll hang out here if you've got any questions.
No shot.
that I'm getting up at 5 o'clock because I don't have class. So I don't have to.
Sorry for walking all the way down.